Okay, good morning grade 11s. This is the final video for Euclidean Geometry, the theorems. And then as I mentioned in the message, I'm going to do one more video on answering exam type questions so that you can see how we do it. Then you can have a little bit of time to practice exam questions on your own. And then hopefully by Wednesday latest, if not, if you still don't feel ready, we can maybe push it to Friday. I'll send you a short assessment that you can do and submit to me. And I'll give you a time limit to do it. We'll figure out when you're not working. That'll just make it a lot easier just for me to gauge if you understand this. It's not going to be for marks, so I don't want you to stress about it, but I do want to see if you understand Euclidean geometry. Okay, so this is theorem 7. It's called the tan chord theorem, or what I like to call the 1, 2, 3, 4 method. And it's probably the most difficult one, so I got a whole bunch of highlighters here just to make my life a bit easier, because it really helps if you highlight what you are doing. Okay, so I'll get to the proof in a second, but first of all you need to know what you are proving. Okay, so it always involves a tangent, and it's sort of like a triangle in the circle, but what you're basically showing, okay, is that this angle over here, so there's two different ones here that work, this angle over here is equal to this angle over there. And the same can be said about, I'll highlight it now, this angle over here, okay, and this angle over there. So it says the angle between a tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment. Now that sounds very complicated and very confusing, hence why I call it the 1, 2, 3, 4 method, okay? And it's hard to know when you just look at this to remember which angle goes with which angle and why they're equal. Okay, so what I like to do is, if you are working around, let's say you want to play with this one, the C2 over here. You want to know what that's equal to, okay? We are going to count. I'll draw it in a second, but you start with the actual angle. So you see this is your angle here, C2. So you're going to start over here and you're going to count 1, okay, 2. And between 1 and 2, you are creating the angle that we are playing around with. We're looking at this angle. So you're going to count 1, 2, okay? Then you go from that part of the circumference to the other part. So you count 1, 2, 3, 4. And when you count 4, you always land back where you started. Okay, it sounds really weird, but I'll give you a few different examples. So 1, 2 gives you the angle that you're working with. 1, 2, okay? Then 3, because 2 will always land on the circumference. 3 must land on another point on the circumference, and 4 must land back where you start. So when you do this, take a highlighter and highlight it in. So it's going to be 1, 2, 3, 4. Do you see what I've done there? And so basically, between 1, 2, so 1, 2, 3, 4, and between 3 and 4, okay, is your angles that are equal. So you count 1, 2. So when you count 1, where you land is your first angle, 1, 2, 3, and when you land at 3, that's your second angle. So just remember 1 and 3 are your two angles. So we are trying to prove here that C2 is equal to A2, okay? I'm going to draw another little one here on the side just to show you again. Okay, let's say this is my tangent, and it looks like this. Okay, which angle is equal to which? So what I'm going to do is I'm going to take a highlighter and I'm going to highlight 1, 2, 3, 4. Now, as you can see, there's two angles here. There's one on this side and there's one on this side. So you can choose. Let's say we want to work with this one. I want to know, what is this equal to? So I'm going to start here. I'm going to count 1, 2 to the circumference, 3 to the other point in the circumference, 4 back where I started. So 1 is here, this angle, 1, 2, here's 3. So it's this angle, 4. So these two angles are equal to each other. Okay, so that's basically what you're going to do when you use the 1, 2, 3, 4 method. But before I can actually work with it, I need to prove this theorem. So that's what we're doing here, required to prove. So they say, they wrote it out nicely here for us, required to prove that BCQ, in other words, this angle C2, that one, is equal to BAC. BAC, this one here. So we are basically the two blue ones that are highlighted. We are going to use that to prove that this theorem is true. Okay, now I know with the other theorems I said most of the time it's using congruency. With this particular one it isn't. It's quite tricky, so I want you to learn it off by heart. Okay, so basically they've started with the construction, they've done it for you. They say draw diameter CD and join AD. So they've drawn this diameter in here, this dotted line, and then they joined DA. Okay, so you'll see in a second why we did that. But before you can even begin, you write required to prove which angles you are showing that they are equal, and then you're going to draw in the diameter and join it to the third point. Remember, 1, 2, 3, 4. So they've joined it to the third point. Okay, so basically when we get started here, like I said, this is something you must parrot fashion. It's not something you can just start and see the logic behind it. So I'm just going to explain it. But do you remember this little thing that we learned? Okay, if this is a diameter and this happens over here, do you remember that this is a 90-degree angle? A diameter subtends a 90-degree angle. You can find that on some of the previous videos we've done. So if you look at this diameter over here, right? Do you agree that if I pull this out like that, it's here on the circumference, do you agree that this A1 and 2 is a 90-degree angle? Because diameter subtends a 90-degree angle. Okay, so that's a little bit of information you can keep in mind there. Do you also agree with me that when you have a tangent and a radius, what happens here? I'll do it in this color. This will also be 90 degrees because tangent is always perpendicular to the radius. So do you see that we've already proved that DAC is 90 degrees and this one over here, this is also 90 degrees. Okay, so we've already started nicely with our proof there, but what we're actually trying to prove is that A2 is equal to C2, but this is a very good starting point, so let's do that. So the first thing we're going to say is angle C1 plus C2. Okay, and I say C1 plus C2 because that's this entire angle here. This is C2 and that's C1, so together it must be C1 plus C2. That is equal to 90 degrees. Why? Because tangent perpendicular to radius. Are you with me? We've got a tangent and we've got a radius, so they must be perpendicular. And I said C1 plus C2 because this little piece of the angle is C1, that little piece is C2, so together they must be C1 plus C2. Okay, then remember, we also did this diameter, this angle's in a semicircle. That's the reason, by the way, if you want to use the diameter subtends a 90-degree angle. Remember, it's always like that. If it's a diameter and the two sides touch the circumference, it means that that will be a 90-degree angle. So I can, and remember this is A1 and A2, so I can go and say angle A1 plus angle A2 is 90 degrees, and that is because angles in a semicircle. You may want to make a summary for yourself on all the different reasons. Maybe I'll do that when I do the revision video from past papers, but it's nice to have all your reasons so that you don't forget them. Okay, but again, I hope you see where I got A1 plus A2 because this piece is A1 and that piece is A2, so together this 90-degree angle is A1 plus A2. Okay, so don't you agree with me that angle C1 plus C2 is equal to angle A1 plus A2. We've just shown that they're both 90 degrees. Okay, but remember the goal here. We're not trying to prove that it's, you know, it's not this whole angle and that whole angle. What we were actually trying to do, and I'll highlight it again, is we are trying to prove that A2 is equal to C2. And I'll count it again for you, remember? 1, 2, 3, 4. So 1 and 3 must be equal to each other. That's what we're trying to prove. We've now gone and proved that this whole huge angle equals that whole huge angle, but we want those little ones. So the next little part is something we did close to the beginning, so you may have forgotten. But do you see that DB subtends this angle A1? And this DB subtends this angle C1. Do you remember that? So look here. Okay, so if I have this, do you remember this? That angle is equal to that angle. If this is AB and it subtends that angle, and it's AB and it subtends that angle, those two angles must be equal to each other. Remember, I called them bow ties, but specifically the reason for that, we say angles in same segment. So I'm going to go ahead and say that angle A1 is equal to angle C1. So angle A1 is equal to angle C1. And the reason being angles in same segment. Remember, angles in same segment is basically fancy talk for bow ties. So DB subtended A1 and DB subtended C1. Okay, so I mean, only logically, if this whole big angle is equal to that whole big angle, and then this little piece of the angle is equal to that little piece of the angle, then surely this angle must equal that angle. Okay, so now you can just say, therefore, angle A2 is equal to angle C2. Okay, and you have proven, you can say, therefore, because that's what we said, BAC is equal to BCQ. And you can always end off with what you started by saying required to prove. Okay, I hope that makes sense. As I've said before, this is the explanation, but mainly you need to know it out of your head. So if you would rather just parrot fashion that, it's a lot to parrot fashion with all the different theorems, so it's good to understand, but basically that is important. And yeah, before I forget, as I did last time, if you are going to use this, the reason that you're going to say is angle between tangent and chord. Okay, so if you want to use this whole theorem, you're going to say angle between tangent and chord. Okay, hope that makes sense. You can copy that down. Alright, I've got 2 examples here for you. The first one's a little bit simpler. And just remember 1, 2, 3, 4. You'll start to get the hang of it when you do this, but otherwise I get very confused about which angle equals which. Okay, I don't know if this is very clear, but they want you to determine x and y. Okay, x is this angle over here, and y is that angle over here. They've also said that this little angle over here is 15 degrees, and this angle is 30 degrees. I hope you can read it, but yeah, so it's 15 and 30. Okay, and they're looking for x and for y. So now this incorporates some of the previous theorems that you've learned. But if you look at this, do you see you've got that kind of little housey look going? Looks like this. Okay, and this is the center, and that's the circumference. Does that not ring a bell about that and that? What was that called again? Or what was the story with that? Remember, it was your angle at your center. It's going to be double the angle at the circumference. So if we're trying to find x here, and that's 30, x would be 30 times 2, which is 60. So I can go ahead and I can say x is equal to 60 degrees because angle at center equals to angle at circumference. This was your rule. That was your reason that you use. So this x must be double the size of that 30 because it creates that little like housey look. Just look for that housey look. Okay, then we need to go and we need to calculate y. Now obviously we've just dealt with theorem 7, so you can see it's a tangent, and you can see a little bit of a 1, 2, 3, 4 thing going. I recognize a tangent, and I recognize it's stuck to a triangle. So what I'm going to do is I'm going to take my highlighter, and I'm going to highlight the 1, 2, 3, 4. Okay. So if you're doing the 1, 2, 3, 4, you must start by making the angle that you're looking for. Okay, so you're looking for y. So it's 1, okay, 2, from circumference to the other point, 3, and back to where you started, 4. Okay, so now that I've done that, make sure you get the correct one. This is 1. Okay, that's angle 1, that's y. 1, 2, 3, 4. Here's 3, it's this whole angle here. Okay, so clearly this y is equal to this whole angle A. Here's A1, and then this little piece is 15. So y is going to be 15 plus whatever this thingy is. Do you see it? Let me just make it a bit bigger here. So basically you've got this. Okay, you've got, this is A1, and this little piece is 15. This whole thing is what we're looking for. So it's going to be 15 plus A1. Okay, so that means we need to go and figure out what A1 is. Do you see that this is an isosceles triangle? Okay, so that's x, but we've already figured out that that is not just x, that is 60. And you've got A1 and C1. But if it's isosceles, you guys know the drill. You say 180 minus that angle, and you divide it by 2, because the two base angles must be the same. Okay, so what I'm going to say is A1 is equal to that C1, right? Because it's an isosceles triangle, which is equal to, and I'm just going to do it in one step, 180 minus 60 divided by 2, which is equal to what? It's equal to 60 degrees. So both these